One point of infrared light appeared beside Alpha Centauri A in August 2024. Then, when the James Webb Space Telescope looked again, it was gone. Not once, but twice. The source, known as S1, could be a cold Saturn-class planet moving through the habitable zone of the nearest Sun-like star, or it could be a rare illusion created by starlight, optics, and imperfect subtraction. The unsettling part is that both explanations still fit the evidence. Where are you watching or listening from? And what time is it there? Leave a comment with your city or country, whether this is part of a late-night wind-down, a study session, or a quiet moment between tasks. Thank you for spending part of your time with Calm Space Science. A gentle like, a subscription, or sharing this video helps the channel continue creating thoughtful journeys through the universe. Now the glare of two nearby suns begins to fade, and the search for the missing world can come into view. Alpha Centauri does not look complicated from Earth. To the unaided eye, it appears as one bright point in the southern sky, steady enough to seem singular. Yet that point belongs to a system whose structure is far richer than its appearance suggests. Alpha Centauri A and Alpha Centauri B form a close stellar pair about 4.3 light-years from the Sun, while Proxima Centauri moves much farther out as the faint third member of the same family. Together, they make the nearest known star system beyond the solar system, a place close enough to occupy a special position in astronomy, but still distant enough that its smallest details remain difficult to recover. Light leaving the system takes more than 4 years to reach Earth. In the scale of the galaxy, that interval is almost nothing. In the scale of any human journey, it is an immense barrier. This contrast gives Alpha Centauri its enduring importance. It is both the nearest example of another stellar neighborhood and a reminder that even the closest stars remain separated by distances that ordinary intuition was never built to hold. The three stars are not interchangeable. Alpha Centauri A is the largest and brightest of the group, a main sequence star of the same broad class as the Sun. Its mass is slightly greater than the Sun's, and its surface is somewhat hotter, giving it a pale yellow-white light. Alpha Centauri B is smaller, cooler, and more orange, though it too is a stable main sequence star rather than an exotic remnant or a young object still forming. The two stars orbit a common center of mass in a long elliptical cycle lasting close to 80 years. At some points in that cycle, they are relatively near each other. At others, they separate by a much greater distance. Their changing geometry creates a planetary environment unlike the quiet isolation of the Sun, because any world around one star exists under the distant but persistent gravitational influence of the other. Proxima Centauri is different again. It is a red dwarf, much smaller and dimmer than either Alpha Centauri A or B, and it lies thousands of astronomical units from the bright pair. An astronomical unit is the average distance between Earth and the Sun, so this outer separation is not comparable to the spacing of planets. It belongs to the scale of a very wide stellar orbit. Proxima is also the closest individual star to the Sun, slightly nearer than Alpha Centauri A and B, which explains its name. Yet proximity does not make it visually prominent. Red dwarfs release far less visible light than stars like the Sun, and Proxima is too faint to be seen without a telescope. The star that is physically closest is therefore almost hidden, while the more distant central pair combines into one of the brightest points in the southern sky. That reversal is the first of many reasons the system resists simple description. Alpha Centauri is often called a triple star, but its architecture is hierarchical rather than compact. Alpha Centauri A and B make the tight inner binary, while Proxima occupies a remote outer path around them. The system is therefore not three stars crowded together at equal distances. It is more like a close partnership with a distant companion held by the same gravitational structure. The exact history of that arrangement is difficult to reconstruct. The three stars probably formed from related material. Yet their present spacing leaves room for questions about how their orbits evolved and how stable planetary systems could emerge within them. Those questions matter because planets do not form around abstract points of light. They form inside disks of gas and dust, whose shapes, lifetimes, and temperatures are influenced by the stars around them. In a binary system, the companion star may truncate a disk, disturb its outer regions, or alter the paths of growing worlds. The existence of a nearby stellar partner does not prevent planets, but it changes the conditions under which they assemble and survive. Alpha Centauri A carries unusual weight within this system because it is the nearest star that resembles the Sun so closely. It is not a perfect copy. Its greater mass and luminosity shift the distances at which temperatures may allow liquid water under suitable atmospheric conditions. Its companion star also makes the environment dynamically different from the solar system. Even so, the resemblance is strong enough to make every planetary question around it feel unusually immediate. Most known exoplanets orbit stars that appear only as remote entries in a catalog. Alpha Centauri A is close enough that its motion, activity, brightness, and surroundings can be examined with a level of attention rarely possible for a Sun-like star. It becomes a natural test case for a larger question whether the architecture of the solar system is common around stars that formed with similar basic properties, or whether familiar arrangements become rare once a stellar companion is introduced. The distinction between Alpha Centauri A and Proxima Centauri is especially important. Proxima already has known planetary companions, including a roughly Earth-mass world on a short orbit. Those discoveries prove that the nearest stellar system is not empty. They do not, however, answer what exists around the two brighter stars. A planet near a red dwarf develops under very different conditions from a planet near a star like the Sun. Red dwarfs are cool and faint, so their temperate zones lie close to the star, where orbital periods are short and tidal effects may be strong. They can also produce energetic flares that alter planetary atmospheres. Alpha Centauri A offers a different experiment. Its light, mass, and long-term energy output are much closer to the conditions that shaped Earth. Even though the presence of Alpha Centauri B adds a second gravitational and luminous influence, a world there would not simply be the nearest exoplanet. It would be part of the nearest planetary system around a close solar analog, a phrase used for a star that resembles the Sun in important physical ways. That is why the search has continued despite repeated frustration. Alpha Centauri is close, but closeness creates its own observational problems. The stars appear bright because they are near, and that brightness can overwhelm the much fainter glow of any planet beside them. The apparent separation between a star and a planet is also small when viewed from more than 4 light-years away. A world as large as Jupiter may shine billions of times less brightly than a Sun-like host in visible light. Even in infrared light, where a cool planet can reveal heat of its own, the contrast remains severe. Alpha Centauri B adds another layer of difficulty because its light enters the same observing field and produces patterns that must be distinguished from any genuine planetary source. The very system astronomers most want to examine is therefore one of the most technically demanding nearby targets, yet its closeness also raises the value of success. A planet detected around Alpha Centauri A could be followed through its orbit on a practical timescale. Its changing position might be measured. Its thermal emission could be compared across multiple observations. Future instruments might separate parts of its spectrum and search for the chemical signatures of an atmosphere, Even when a candidate is a gas giant rather than a rocky world, its existence would reveal how matter organized itself in the nearest sun-like binary. It could also point toward moons, rings, smaller unseen companions, or a broader planetary architecture that current instruments cannot yet resolve. The importance lies not only in the individual object, but in the system it would begin to expose. Alpha Centauri has also become a reference point for the distant future of exploration. Concepts for extremely fast miniature probes often name Proxima or the bright Alpha Centauri pair because no other stellar destination is closer. Such proposals remain far beyond ordinary spacecraft engineering, and even the shortest interstellar journey would demand technologies unlike those used for planetary missions within the solar system. Still, scientific knowledge must come before any journey. Before a probe could ever cross that distance, astronomy has to determine what is there, which stars possess planets, how those planets move, and what environments surround them. In that sense, every careful observation of Alpha Centauri is already part of a much longer approach. The system is being reached first by light, by spectra, by subtle changes in position, and by instruments designed to separate a small planetary signal from the glare of a neighboring sun. Its significance comes from this convergence of familiarity and uncertainty. The stars are near. Their basic properties are well measured. Their relationship to the sun is clear. Yet the planetary landscape around the two brightest members remains largely concealed. Alpha Centauri A may be the nearest stellar relative of the sun, but resemblance does not reveal whether it is surrounded by a similar family of worlds. That answer has remained behind brightness, orbital complexity, and the limits of every instrument directed toward it. For decades, the system has stood close enough to invite certainty and difficult enough to withhold it, turning the nearest stellar neighborhood into one of the longest unresolved searches in modern exoplanet science. The search for planets around Alpha Centauri did not begin with a single dramatic observation. It developed through decades of measurements that were often precise enough to suggest something and rarely decisive enough to settle it. The difficulty is built into the system itself. Alpha Centauri A and Alpha Centauri B are bright, nearby, and constantly changing their apparent relationship as they move through their long binary orbit. A planet around either star would add a much smaller motion to an already complicated pattern, while the light from the companion star would continue to enter the same instruments and the same calculations. Astronomers therefore faced a target that was attractive for exactly the reasons it was difficult. Its nearness made small planetary effects more accessible, but its brightness and binary structure made those effects easier to confuse with something else. Early searches relied heavily on astrometry, the measurement of a star's position against the sky. A planet does not orbit a perfectly fixed star. Star and planet move around a shared center of mass, causing the star to trace a tiny reflex motion. For a massive planet on a wide orbit, that motion can be large enough to matter. Around Alpha Centauri, however, the expected planetary signal had to be separated from proper motion across the sky. Parallax caused by Earth's orbit around the Sun, and the far stronger motion of the two stars around each other. Each effect unfolds on a different timescale, and any small error in one model can leak into the others. The result is not simply a matter of taking a sharper picture, it is a problem of disentangling several motions that occupy the same data. As spectrographs improved, radial velocity became another major route. This method searches for small shifts in a star's spectrum as it moves slightly toward and away from Earth under the pull of an orbiting planet. The principle is simple, but the measurement is not. A sun-like star does not provide a perfectly stable reference. Convection moves hot material through its surface. Dark star spots rotate in and out of view. Bright magnetic regions alter the balance of light across the stellar disk. Oscillations change the shape of spectral lines over short intervals. In a binary system, contamination from the companion star may add another pattern. A signal that looks periodic can therefore arise from a planet, from stellar activity, from the timing of the observations, or from the mathematical treatment used to remove known effects. Alpha Centauri became one of the clearest examples of how these possibilities can imitate one another. In 2012, researchers announced evidence for a small planet orbiting Alpha Centauri B. The proposed world, commonly called Alpha Centauri BB, appeared to complete an orbit in just over 3 days. Its estimated minimum mass placed it near the terrestrial range, and the announcement immediately drew attention because it seemed to locate an Earth-mass planet around one of the 2 nearest Sun-like stars. The orbit would have been far too hot for surface conditions like those on Earth, but that was not the main significance. If one small planet existed there, others might also have formed in the system. The detection seemed to turn a long-standing possibility into something concrete. Yet, the signal sat close to the limits of the data. Later analyses showed that the observing schedule and the removal of longer period patterns could produce an artificial peak near the proposed orbital period. What had looked like a coherent planetary rhythm could emerge from the window function, the pattern created by when observations are made and when they are missing. The planet was never independently confirmed. Over time, Alpha Centauri B became a cautionary case rather than an accepted world, not because the original work lacked care, but because extreme precision can expose the structure of the observing process as clearly as it exposes the star. The lesson was broader than one disputed signal. When the expected motion is comparable to the combined effects of noise, stellar variability, and sampling, statistical significance alone is not enough. The signal has to survive different instruments, different analysis methods, and new observations gathered at times when the proposed orbit makes a clear prediction. Alpha Centauri has repeatedly offered hints that were interesting at first and unstable under that kind of pressure. Some searches found weak periodicities that could be matched to possible planets, but also to stellar rotation or magnetic cycles. Others set useful limits by showing what kinds of planets were not present on certain orbits. A non-detection may seem less satisfying than a discovery, yet it gradually changes the map of what can still exist. Large, close-in planets became harder to hide. Certain orbital configurations were ruled out. The remaining possibilities shifted towards smaller worlds, wider paths, lower masses, and signals that required longer baselines or different wavelengths. Direct imaging introduced another set of obstacles. A planet reflects very little visible light compared with its star, and even a giant planet emits only a faint thermal glow once it has cooled for billions of years. Alpha Centauri A and B are mature stars, so any planets around them are likely to be mature as well. They would not possess the intense heat of young gas giants that are easier to image around distant, recently formed stars. The nearest system, therefore, asks instruments to find colder and dimmer planets than many of the worlds already photographed elsewhere. At the same time, the angular distance between a possible planet and its host remains small. Nearness helps by spreading a given orbital separation across a slightly larger angle on the sky. But the improvement is not enough to remove the glare. The image still contains diffraction, detector effects, imperfect wavefronts, and light from the second star. A planetary point source must remain consistent after all of those structures are modeled and subtracted. The search around Proxima Centauri developed along a different path. Because Proxima is far dimmer and much less massive, a low-mass planet can produce a larger radial velocity effect, and its temperate region lies close to the star, Proxima b, the best established planet in that part of the system. Orbits in roughly 11 days and has a minimum mass in the same broad range as Earth. Its discovery showed that a nearby planetary signal could be recovered with repeated spectroscopy, but it did not solve the problem around Alpha Centauri A or B. The stars are physically different. The orbital scales are different, and the observational backgrounds are different. A planet in the temperate region of Proxima lies close to a magnetically active red dwarf. A planet receiving comparable heating from Alpha Centauri A would orbit much farther out over a much longer period, while competing against the glare of a star more luminous than the Sun and the additional light of Alpha Centauri B. The known planet around Proxima therefore demonstrated that the nearest system forms planets. But it did not make the bright pair easier to search. Instead, it sharpened the contrast. One part of the system yielded through radial velocity measurements, while the central pair remained resistant across methods. By the time a new generation of infrared instruments became available, the question had changed. Astronomers were no longer asking only whether any planet might exist around Alpha Centauri A. They were asking which region of mass, temperature, and orbital distance had escaped every previous search, and which method could enter that remaining space. Radial velocity was most sensitive to certain combinations of mass and period. Astrometry required a long and stable record. Visible light imaging faced extreme contrast. Thermal infrared imaging offered a different advantage because a cool planet could reveal its own heat rather than depend entirely on reflected starlight. That approach did not erase the old difficulties, but it shifted them into a form that could be attacked with new detectors, coronagraphs, and image processing. The decades of frustration were therefore not empty. They defined the boundaries of the problem. They showed how easily a planet-like signal could appear, how much evidence was needed before it could be trusted, and why Alpha Centauri demanded an instrument able to work where earlier searches had left only a narrow opening. When James Webb turned toward the system, it entered a field already shaped by false starts, missing confirmations, and increasingly precise limits. The next signal would not be judged by whether it looked promising once. It would be judged by whether it could survive the history of everything that had looked promising before. James Webb enters the Alpha Centauri search with an advantage that is easy to describe and difficult to achieve. It can look for heat. Most planets are almost invisible beside their stars in ordinary light because they do not produce much visible radiation of their own. They shine mainly by reflecting a tiny fraction of the light that reaches them, while the star beside them remains millions or billions of times brighter. A mature giant planet around Alpha Centauri A would be especially challenging in that regime. The system is old enough that any large world there should have cooled far below the temperatures of the young planets commonly photographed around recently formed stars. In visible wavelengths, such a planet would be little more than a weak mirror. In the mid-infrared, however, it can become a source in its own right. Every object with a temperature above absolute zero emits thermal radiation. For a cool planet with a temperature of a few hundred Kelvin, much of that emission appears at wavelengths longer than the human eye can detect. This changes the contrast problem. The star is still overwhelmingly bright, but the difference between star and planet becomes less severe than it is in visible light, and the planet's signal carries information about its own temperature rather than only about the light falling on it. That is the reason the mid-infrared instrument, known as MIRI, is central to Webb's attempt. MIRI observes wavelengths where cold dust, planetary atmospheres, and the thermal glow of cool worlds can emerge from backgrounds that would hide them at shorter wavelengths. For Alpha Centauri A, the relevant observations use light near 15.5 micrometers, a range suited to detecting emission from a mature giant planet with temperatures far below those of stars. The instrument is not simply a camera working in a different color. Mid-infrared astronomy has to manage a universe of warm objects. The telescope, its instruments, and even material near the line of sight can produce infrared emission. Webb was therefore built to operate cold, far from Earth, behind a large sunshield that keeps sunlight, Earthlight, and much of the spacecraft's own heat away from the mirrors and detectors. Its position near the second Sun-Earth Lagrange point allows the Sun, Earth, and Moon to remain in roughly the same direction, so the shield can block them together. That thermal stability is one of the hidden requirements behind the search. A telescope trying to detect a planet at a few hundred Kelvin cannot itself behave like a warm, changing source. Webb's cryogenic design lowers the background enough for MIRI to measure faint mid-infrared signals with the precision required. Yet cold detectors alone do not solve the central problem, because Alpha Centauri A remains directly in the field. Its light has to be suppressed before a planet can be recovered nearby. MIRI carries coronagraphs designed for this purpose. A coronagraph is an optical system that blocks or redirects the bright core of starlight so that much fainter structures close to the star can be examined. The principle resembles placing a small screen over a distant lamp, but the real instrument has to control diffraction, the spreading and interference of light around edges and through apertures. A star is not removed simply by covering its central image. Its light forms rings, spikes, and complex patterns determined by the telescope's segmented mirror, support structures, optical alignment, and observing wavelength. Those patterns can extend into the region where a planet is expected. The coronagraph reduces the dominant glare, but it does not leave a perfectly black field. It creates a residual landscape that has to be calibrated, modeled, and compared for the Alpha Centauri observations. This is particularly demanding because the target is one of the brightest stars Webb can observe in this mode. Brightness is usually an advantage in astronomy, but here it becomes a source of precision problems. Tiny pointing errors can shift the star relative to the coronagraph. Small changes in the telescope's wavefront, the shape of the incoming light across the mirror, can alter the remaining speckle pattern. Detector behavior can become more important when the central source is so intense. A candidate planet must therefore appear not as a convenient point in a clean image, but as a stable excess embedded in structured leftovers from the star. MIRI's value lies in the way its hardware and wavelength range work together. The coronagraph lowers the direct stellar contribution. The mid-infrared detector looks for the planet's own heat. Webb's large mirror gathers enough light to make the faint source measurable. Its stable location and cold architecture reduce thermal noise. None of those elements would be sufficient alone. A large mirror without suppression would collect more glare. A coronagraph without infrared sensitivity would still face the severe reflected light contrast of a mature planet. A cold infrared detector without angular resolution would blend star and planet together. The search becomes possible only when these capabilities overlap in the same observation. The nearby distance of Alpha Centauri then begins to help. A planet orbiting at a few astronomical units from Alpha Centauri A appears farther from its star on the sky than an equivalent planet around a more distant system. The separation is still small, but it can fall outside the innermost region where the coronagraph is least effective. This is one reason the system is such an important test. Webb was not designed as a dedicated telescope for imaging Earth twins around Sun-like stars. Its coronagraphs and infrared instruments were built for a range of targets, including young planets, dust disks, and distant galaxies. Alpha Centauri offers a chance to push those capabilities toward an older, colder, and more familiar planetary regime. Instead of observing a glowing young world that is still radiating heat from formation, Webb can search for a mature planet whose temperature reflects a quieter balance between internal heat and energy received from its star. That distinction matters because most planetary systems in the galaxy are not newly formed. They are old enough for their giant planets to have cooled, their disks to have thinned, and their early brightness to have faded. A technique that works only for youth samples an unusual stage. A technique that can reach mature worlds begins to approach the conditions of nearby systems as they exist now. MIRI also carries an advantage in how planetary brightness can be interpreted. A source at 15.5 micrometers can be compared with atmospheric and evolutionary models to estimate what combinations of radius, temperature, cloud structure, and composition might reproduce the measured flux. Those estimates remain uncertain, especially from a single wavelength, but they turn a point of light into a physical question. A colder, larger object can sometimes resemble a warmer, smaller one. Atmospheric absorption can suppress one part of the spectrum and enhance another. Clouds can change how heat escapes. Even so, thermal emission places constraints that reflected light alone cannot provide. It begins to reveal whether a candidate behaves like a planet rather than merely occupying a planetary position. The method also has limits that shape every conclusion. MIRI cannot directly show a globe, atmosphere, or surface at Alpha Centauri. A planetary candidate remains unresolved, smaller than a single image element, and appears only as a point source. The instrument measures brightness and position, not a detailed portrait. A source can also be confused with background objects. Residual optical structure, detector artifacts, or dust emission, unless repeated observations show consistent motion and behavior. The coronagraph creates blind regions where a planet may pass too close to the star's apparent position to be recovered. The telescope's orientation changes which diffraction structures fall across the field. Each observation is therefore a partial view shaped by geometry. This is why Webb's first look could produce a meaningful candidate without producing immediate certainty. The instrument was capable of entering a region of mass, temperature, and separation that earlier searches had struggled to reach. But it could not remove every ambiguity in a single visit. Its achievement was narrower and more important than a simple claim of discovery. Webb demonstrated that a mature, relatively cool world near the nearest sun-like star could produce a detectable signal in the mid-infrared after the star's light was suppressed. That possibility had existed in models and observing proposals. With MIRI, it became an actual measurement problem. The target was no longer merely too faint beside a brilliant star. It was faint in a way that could be isolated, tested, and followed. The next challenge was to determine whether the isolated point belonged to a planet, to the instrument, or to the complicated field left behind when two neighboring suns were partially erased. The most difficult part of observing Alpha Centauri A is not collecting its light. It is preventing that light from becoming the only thing the instrument can see. The star is bright enough that every imperfection in the telescope leaves a visible trace around it, and those traces occupy the same region where a planet must appear. A coronagraph reduces the central glare, but the remaining field is still filled with structured light. Diffraction produces rings and lobes. The segmented primary mirror creates its own repeating geometry. Small differences in optical alignment leave faint speckles that can resemble point sources. Detector behavior adds patterns that are not part of the sky at all, around a solitary star. These effects are already demanding. Around Alpha Centauri A, they are joined by Alpha Centauri B, whose light enters the observation from a nearby but separate position and spreads across the detector in a second family of features. The task is therefore not merely to hide one star. It is to understand how two stars, one coronagraph, one segmented telescope, and one infrared detector combine to manufacture a false landscape of light. Alpha Centauri A remains the central target. So, the observing sequence places it behind MIRI's coronagraphic mask with extreme care. The mask is designed to suppress the star's core and reduce the strongest diffraction close to its position. But its performance depends on centering. A small pointing offset changes how much starlight leaks around the mask and where that leaked light appears. Webb can point with extraordinary precision. Yet the search for a faint planet requires more than the precision normally associated with locating a distant object. The relevant question is whether the star occupies nearly the same position relative to the optical system during the science observation and every calibration used to remove it. Even a tiny mismatch can produce a bright residual after subtraction. What remains may have the size and shape expected from a point source, especially when the signal is weak. That is why the image cannot be interpreted by eye alone. Each apparent feature must be tested against a model of how the telescope would respond if no planet were present. Alpha Centauri B complicates that model because it is not hidden in the same way. Its angular separation from Alpha Centauri A changes over the binary orbit, and during the Webb observations, it lies outside the coronagraphic center. The companion therefore contributes light through the telescope from an off-axis position. Off-axis light creates a pattern different from the suppressed central star. But it is not harmless. It can generate broad diffraction structures, scattered light, and detector response across regions that would otherwise be searched for planets. Some of these features may cross the expected orbital zone around Alpha Centauri A. Others may change with telescope orientation, causing a bright patch to appear in one visit and shift in another without any object moving through space. A valid search must separate changes caused by orbital motion from changes caused by the geometry of the instrument. The researchers therefore treated the binary system as part of the optical problem rather than as a simple background complication. The light of Alpha Centauri A and the light of Alpha Centauri B had to be modeled together, because removing one without accounting for the other could leave residuals that falsely suggested a third source. The process begins with calibration stars and reference observations chosen to resemble the target in brightness and spectral behavior as closely as possible. A reference star observed through the same coronagraph produces its own pattern of diffraction and speckles. In an ideal instrument, subtracting that pattern from the target image would remove the stellar light perfectly. Real observations never align so cleanly. The reference may have a slightly different spectrum, which changes the balance of light across the instrument's bandpass. The telescope's optical state may shift between visits. The centering behind the mask may differ by a small amount. Thermal conditions may not be identical. Each difference leaves residual light, rather than assuming one reference image is correct. The analysis can combine multiple reference patterns and adjust their weights to reproduce the target field. This creates a flexible model of the stellar point spread function. The characteristic way a point source is distributed by the telescope, the model is then subtracted, leaving whatever cannot be explained by the expected behavior of the stars and the instrument. Yet flexibility introduces its own danger. An algorithm powerful enough to remove complex starlight may also remove part of a real planet. If a faint source lies within the region used to optimize the subtraction, the model may treat that source as another feature to erase. This effect, often called self-subtraction or overfitting, reduces the measured brightness and can distort the apparent shape of the candidate. The analysis must therefore test how artificial planets behave when inserted into the raw data. Synthetic sources with known positions and brightnesses are passed through the same processing steps. Their recovery shows how much signal the algorithm preserves, how accurately it measures position, and where the search becomes unreliable. This is essential near the coronagraph, where the stellar residuals are strongest and the response changes quickly with distance. A candidate cannot be evaluated only by how bright it appears after processing. It has to be corrected for how much of an equivalent signal the processing would have removed. The same tests also reveal the pattern of false detections. Noise in a coronagraphic image is rarely uniform or perfectly random. Close to the star, a small number of bright residual structures may dominate. Farther out, detector noise and background emission may matter more. Alpha Centauri B adds regions where the noise rises again because its off-axis diffraction crosses the field. Statistical significance, therefore, depends on location. A point that looks unusual in a quiet part of the image may be ordinary in a region filled with speckles. Researchers estimate the local background by comparing the candidate with other resolution elements at similar separation from the star, while also accounting for the small sample of independent positions available near the center. The aim is not to force the image into a simple measure of certainty, but to ask how often the same pipeline produces a signal of comparable strength where no planet is expected. Rotating the telescope provides another way to test the field. A real astronomical source remains fixed relative to the stars, while many optical patterns rotate or change relative to the sky when the observatory's orientation changes. In practice, the distinction is not always complete, because the coronagraph, detector, and binary geometry interact in complicated ways. Still, observations at different orientations help separate sky features from instrument features. The analysis can align the images on Alpha Centauri A and examine which structures remain at a consistent celestial position. It can also model the contribution from Alpha Centauri B at each orientation. Since the companion's diffraction pattern moves across the detector, even though the star itself remains in the same place on the sky, this repeated remapping of light is one reason the final image is not a single exposure. It is a constructed result assembled from many frames, calibrations, transformation, and rejection tests. At every stage, the possibility of a planet has to survive choices that were designed before its exact position was known. The strongest protection against wishful interpretation is to run more than one reasonable method. Different subtraction approaches may use different reference combinations, optimization regions, or treatments of the binary companion. If a point source appears only under one narrow set of assumptions, confidence remains low. If it survives independent processing paths and retains a consistent location and approximate brightness, the case becomes stronger. Even then, the result is not automatically physical. Residual detector artifacts can persist. Background galaxies can appear point-like at limited resolution. Dust around the star could create uneven emission. A single visit can establish that a feature is difficult to remove, but not that it is orbiting Alpha Centauri A. The analysis around this system, therefore, has an unusual character. It is partly astronomy and partly forensic reconstruction. The raw image contains the stars, the telescope, the detector, the coronagraph, and the sky superimposed. The goal is to account for each known contributor without erasing an unknown one. Only after the light of Alpha Centauri A is suppressed. The off-axis influence of Alpha Centauri B is modeled. The diffraction field is subtracted. The detector behavior is calibrated, and the processing losses are measured. Does the planetary search truly begin? What remains is not a clean view of another solar system. It is a small set of residuals that have resisted explanation, among them, in the first observing epoch. One point stood apart strongly enough to receive a name, S1. Its importance came not from appearing in an untouched image, but from remaining after two brilliant stars, and the instrument between them had been mathematically removed as carefully as the data allowed. In August 2024, the long search around Alpha Centauri A narrowed to a single point of light. It did not arrive as a vivid image of a world, and it did not resemble the familiar pictures of planets taken within the solar system. It appeared instead as a compact residual in processed mid-infrared data, a small source left behind after the dominant light of Alpha Centauri A, the off-axis influence of Alpha Centauri B, and the known structures of the instrument had been reduced as far as the analysis allowed. The source was labeled S1. Its position placed it about 1.5 arcseconds from Alpha Centauri A, an angular separation that corresponds to a projected distance of roughly 2 astronomical units at the system's distance. That location immediately made the signal interesting, because it falls within the broad region where a cool giant planet could orbit a star slightly more luminous than the Sun. Yet, position alone could not establish what S1 was. A background object could appear in the same direction. A residual speckle could survive the subtraction. A detector artifact could imitate a point source. The significance of the observation came from the way several lines of evidence converged without becoming decisive. S1 appeared point-like. It emerged in a wavelength band chosen to reveal thermal emission from cold planets, and its brightness was compatible with a mature giant world rather than with a hot young object still glowing from formation. At the same time, it was found only in one observing epoch, which meant every interpretation had to remain provisional. The first question was whether the location made physical sense. At about 2 astronomical units from Alpha Centauri A in projection, the source occupied a region comparable in scale to the space between Mars and the outer asteroid belt in the solar system. Although the comparison is only geometric, Alpha Centauri A is brighter than the Sun, so the amount of energy received at a given distance is greater. A world there would experience a different thermal balance, and the true orbital distance could be larger than the projected separation because an image compresses three-dimensional space into a flat plane. The object might be closer to the star along the line of sight or farther away, with only part of its orbital radius visible in the image. Even so, the observed separation was not arbitrary. It fell within the range where the coronagraph could suppress much of the stellar glare while still allowing a planetary signal to emerge, and it also lay within a region of strong scientific interest around the star. The second question was whether the brightness behaved like a real source. The observations were made near 15.5 micrometers, where a cool planet can radiate a measurable amount of heat. In the processed data, S1 was not overwhelmingly strong. Its reported statistical significance varied depending on the method used to remove starlight and estimate the surrounding noise, falling roughly between 3.3 and 4.3 sigma. Sigma is a measure of how unusual a signal is compared with the expected fluctuations in the data. A larger value usually suggests that random noise is less likely to produce the result. Yet coronagraphic images do not contain simple, perfectly independent noise. The residual field is structured. Speckles can be correlated. The number of comparison regions near the star is limited. A value that would appear persuasive in a large, clean dataset must be treated more cautiously when only a small number of independent resolution elements are available and the noise changes with position. The range in significance therefore mattered as much as the upper value. It showed that S1 survived different processing choices. but it also showed that the strength of the detection depended on how the stellar background was modeled. A real planet near the threshold of detectability can behave in exactly that way. So can an especially persistent optical residual. This ambiguity defined the candidate from the beginning. Its shape offered another clue. After correction for the way the processing attenuated point sources, S1 resembled the telescope's expected response to an unresolved object. It did not appear as a broad cloud or a long streak. That point-like form was consistent with a distant planet, because even a gas giant around Alpha Centauri would be far too small for Webb to resolve as a disk. But point-like does not mean planetary. Distant galaxies can appear compact. Instrumental structures can concentrate into false points. The source, therefore, had to be considered in relation to the wider field. Researchers examined whether similar residuals appeared elsewhere at the same separation, whether the signal persisted under alternative subtraction strategies, and whether artificial planets inserted into the data were recovered with comparable shapes and brightness. Those tests strengthened the case that S1 was not an obvious processing accident. They did not remove the need for another observation. The timing of the detection added quiet pressure. The August epoch provided a single snapshot in a system where any genuine planet should move. Around a star like Alpha Centauri A, an object at a few astronomical units could complete an orbit in only a few years. Its position might change measurably over several months. That motion could become the clearest test available, because a true companion should follow a path tied to the star, while a distant background object would show a different apparent displacement as Alpha Centauri moved across the sky. Alpha Centauri has a large proper motion, meaning that its position relative to remote background sources changes noticeably from year to year. This normally complicates long-term measurements, but it also creates leverage. A source physically bound to the star should travel with it. A background galaxy should not. Repeated imaging could therefore transform a faint point into an orbital arc or expose it as an unrelated object. The difficulty was that the first image contained no history. S1 had a position, but not yet a trajectory. Its designation reflected that restraint. It was a source, not a named planet. The label preserved the observation without granting it a nature the data had not established. This distinction is central to how exoplanet candidates are handled. A signal can be scientifically important before it is confirmed. It can guide new observations, constrain possible orbits, and reveal what an instrument is capable of detecting. But confirmation requires the signal to behave consistently through time. For direct imaging, that usually means recovering the source again, measuring motion compatible with a bound orbit, and showing that its brightness and spectrum remain physically plausible. One image can suggest it cannot trace. The possibility of contamination also had to remain open. At mid-infrared wavelengths, the background sky contains galaxies, dusty objects, and other sources that may be invisible or faint at shorter wavelengths. The chance of one aligning near Alpha Centauri A is small, but not zero. The local environment around the star may also include exozodiacal dust, the distant equivalent of the diffuse dust that fills the inner solar system. Uneven dust emission can create structures. Although S1's compact appearance made a simple, diffuse explanation less natural, instrumental origins remained possible as well, especially because Alpha Centauri is an extreme target for the observing mode. Very bright stars can expose detector behavior and optical leakage that are difficult to reproduce with ordinary calibration targets. A residual unique to that geometry could survive even careful subtraction. The strongest reason S1 drew attention was therefore not that every alternative had been eliminated. It was that none of them provided an immediate, effortless explanation. The source occupied a plausible planetary separation, appeared at a wavelength appropriate for a cool giant, survived multiple reductions, and reached a significance high enough to justify serious follow-up. At the same time, it remained close enough to the detection threshold that caution was unavoidable. This balance is where many important discoveries begin. The evidence is too structured to ignore, but too incomplete to accept at face value. S1 became a scientific problem because it stood between those two states. The first observation did not reveal a planet in the ordinary sense. It revealed a candidate pattern that behaved enough like a planet to demand a future. In the image from August 2024, Alpha Centauri A was no longer merely a bright star with empty space around it. For one epoch, at one position, and in one narrow band of thermal light, the system contained an additional point that the known models did not fully remove. Everything that followed would depend on whether that point could appear again. The brightness of S1 does not point toward a small rocky world. At 15.5 micrometers, the source appears more consistent with a cold giant planet, a world large enough to radiate a detectable amount of heat even after billions of years of cooling. This interpretation begins with a simple physical fact. Planets do not stop emitting energy when they cease to be young. A mature gas giant continues to release heat from its interior, left over from formation and maintained by slow gravitational contraction, while also absorbing and re-radiating energy from its star. The balance between those two sources determines how bright the planet appears in the infrared for an object around Alpha Centauri A. The measured signal from S1 can be reproduced by models of a world with a temperature near 225 Kelvin and a size comparable to the large outer planets of the solar system. That temperature is cold by terrestrial standards, but it is not unexpectedly cold for a giant planet receiving moderate stellar energy at a distance of roughly a few astronomical units. It lies above the effective temperatures of Jupiter and Saturn because Alpha Centauri A is more luminous than the Sun and because the candidate may receive more external heating than those distant solar system giants. Yet temperature alone does not identify the object. A planet's infrared brightness depends on radius, atmospheric composition, cloud structure, internal heat, and the efficiency with which radiation escapes. Several combinations of those properties can produce similar emission at one wavelength. The available data, therefore, supports a range of possible physical states rather than a single exact model. Within that range, one plausible interpretation gives S1 a mass between roughly 90 and 150 times the mass of Earth. This places it near the broad territory occupied by Saturn rather than Jupiter, although mass and apparent size do not scale in a simple way for giant planets. Saturn contains far less mass than Jupiter, but still has a radius only moderately smaller. Once a planet gathers enough hydrogen and helium, adding more mass compresses the interior as well as enlarging it. A Saturn mass planet and a Jupiter mass planet can therefore present surprisingly similar visible dimensions, even while their densities and gravitational fields differ. This means a world with the estimated mass of S1 could appear close to Jupiter in radius while remaining much closer to Saturn in mass. The distinction is important because the phrase Jupiter-sized can easily suggest Jupiter-like in every respect. The models do not support that level of certainty. They suggest a large gaseous body, but they do not yet reveal whether its atmosphere, core, composición, cloud layers, or internal heat resemble those of any specific planet in the solar system. A cold giant around Alpha Centauri A would have formed in a disk shaped by both the primary star and Alpha Centauri B. That environment may have influenced how much gas the planet acquired and where it finally settled. In standard models of giant planet formation, a solid core grows first within the surrounding protoplanetary disk. If that core becomes massive enough before the gas disappears, it begins drawing in hydrogen and helium rapidly. The outcome depends on timing. A core that grows slowly may remain a Neptune-class planet with a substantial but limited atmosphere. A core that reaches the critical stage early may become a much larger gas giant, around a binary star. The disk can be disturbed, truncated, or heated by the companion, possibly changing the supply of material and the time available for growth. A Saturn-class world around Alpha Centauri A would therefore carry information not only about one planet, but about the efficiency of giant planet formation in the nearest binary system. The proposed temperature of about 225 Kelvin also deserves careful interpretation. Effective temperature does not describe a single atmospheric layer or surface condition. It is the temperature a simple radiating body would need in order to emit the observed amount of energy. A real giant planet may contain much warmer regions at depth and colder regions high in its atmosphere. Clouds can trap heat beneath them while reflecting incoming starlight. Gases such as methane, water vapor, ammonia, carbon monoxide, and carbon dioxide can absorb strongly at certain infrared wavelengths, changing which layers are visible to a telescope. The 15.5 micrometer measurement samples only part of that complex spectrum. A bright point in this band could arise because the atmosphere emits efficiently there, because the planet is warmer than assumed, because its radius is larger, or because the models do not yet capture the full range of cloud behavior. That uncertainty does not weaken the planetary interpretation in a simple way. It means the same signal can correspond to several types of giant world, without measurements at additional wavelengths. The physical estimates remain linked together. Radius affects temperature. Temperature affects inferred luminosity. Atmospheric chemistry affects how that luminosity emerges. Mass then enters through evolutionary models that describe how giant planets cool over time. The age of the Alpha Centauri system is believed to be several billion years. So, a genuine planet, there should be mature, its formation heat would have declined greatly, leaving irradiation and slow internal cooling as the dominant sources of emission. Evolutionary models can estimate how bright a planet of a given mass should remain at that age. But those models carry uncertainties in composition, core mass, atmospheric opacity, and early thermal history. A planet that formed through a hotter beginning may retain more energy than one that began in a colder state. At young ages, this difference can be dramatic. At mature age, it is reduced but not erased. The inferred mass range for S1 is therefore a model-dependent estimate, not a direct measurement. No gravitational effect has yet been isolated strongly enough to weigh the candidate. No spectrum has yet revealed its atmospheric composition. No resolved image has measured its radius. The mass comes from asking what kind of old giant planet could produce the observed mid-infrared flux under plausible assumptions. That reasoning favors a substantial gaseous world because smaller planets would struggle to emit enough thermal radiation at the measured level. A rocky planet at the same temperature would have a much smaller radiating area. To match the brightness, it would need to be far hotter, much larger than expected for a rocky composition, or surrounded by an unusually extended and luminous atmosphere. Those possibilities are less natural than a gas giant. A warm dust clump could also emit in the mid-infrared, but the point-like appearance and the absence of obvious extended structure make a compact object more compelling. A distant background source remains possible, yet its brightness, location, and survival through the processing keep the planetary explanation competitive. The most interesting feature of that explanation is that S1 would not be a young, self-luminous giant of the kind most often seen through direct imaging. It would be a cold, evolved planet close to a mature sun-like star. Many directly imaged exoplanets orbit far from their hosts, often at distances much greater than the orbit of Neptune. Because wide separations make them easier to distinguish from stellar glare, they are also frequently young, allowing them to shine strongly in the infrared. S1, by contrast, would occupy a much more compact orbit and emit far less internal heat. Detecting such a world would show that Webb can reach into a planetary regime closer to the architecture of ordinary, mature systems. It would not yet reach Earth analogs, which are smaller, cooler, and vastly fainter. But it would move direct imaging away from only the hottest and widest giants. That shift matters because cold giants may influence the entire structure of a planetary system. Their gravity can shape belts of small bodies, scatter comets, alter the orbits of neighboring planets, and constrain where stable, rocky worlds might exist. In the solar system, Jupiter and Saturn played major roles in redistributing material during formation. A Saturn-class planet near Alpha Centauri A could have produced similar effects, although the companion star would add another source of long-term perturbation. The candidate's possible mass is large enough for it to dominate nearby space, but not so large that it approaches the regime of brown dwarfs. Objects formed with much more mass and sometimes through different pathways. It would remain clearly planetary under ordinary definitions if the models are correct. The difficulty is that the models are being asked to explain one point of light at one wavelength from one observing epoch. They can show that a cold giant planet is physically plausible. They cannot prove that the source is one. The temperature near 225 Kelvin, the estimated mass near the Saturn range, and the roughly Jupiter-scale radius form a coherent picture. But coherence is not confirmation. It is an interpretation that fits the evidence without exhausting every alternative. S1 became compelling because the infrared signal did not require an exotic planet. It required a kind of world already known in principle, placed around the nearest close relative of the Sun. The extraordinary part was not the proposed object itself. It was that such an ordinary giant, old and cold and hidden beside a bright star, may finally have become visible. The phrase habitable zone carries more meaning in public imagination than it does in planetary science. Around Alpha Centauri A, it refers to a range of orbital distances where a world with suitable atmospheric pressure and composition might maintain liquid water at its surface. The definition is useful, but it is narrow. It does not identify an ocean, detect a climate, reveal a surface, or establish that life is present. It describes an energy balance, a region where the amount of starlight received is neither obviously too great nor obviously too small for liquid water, under certain assumptions. S1 appears near that region in projection, which gives the candidate unusual importance. Yet, the same fact can be misunderstood if orbital location is treated as a complete description of a planet. A gas giant can pass through a habitable zone without becoming habitable in the terrestrial sense. Its atmosphere may contain pressures and temperatures far beyond anything found at Earth's surface. It may have no solid boundary at all, only deeper layers where gas gradually becomes fluid under immense compression. The zone says something about the star and the orbit. It says much less about the body occupying that orbit. Alpha Centauri A is slightly more massive and more luminous than the Sun, so its habitable zone lies farther outward than the corresponding region in the solar system. A planet at roughly the same distance as Earth would receive more energy there than Earth receives from the Sun. The region where temperate conditions might be possible therefore shifts outward, although the exact limits depend on the atmosphere being considered. A world with a thin atmosphere, a dense carbon dioxide atmosphere, or a bright reflective cloud layer can respond very differently to the same amount of starlight. Climate models often distinguish between a conservative habitable zone, where a rocky planet with an Earth-like atmosphere might plausibly maintain liquid water, and a wider optimistic zone based on less restrictive assumptions. These boundaries are not sharp walls in space. They are model-dependent transitions. A planet does not cross one exact line and suddenly become habitable. Its climate changes through feedbacks involving clouds, water vapor, ice, carbon dioxide, and surface properties. The orbital position of S1 is therefore best understood as compatible with temperate stellar heating, not as evidence of an Earth-like environment. The candidate's projected separation of about 2 astronomical units places it in a region where the incident energy could be significant but not overwhelming for a cool giant. Because the measured separation is only the distance across the plane of the sky, the true orbital radius may be larger. The planet could lie partly in front of or behind the star from Earth's perspective. An eccentric orbit could also carry it through a wide range of distances, changing the energy it receives during each revolution. A single image cannot reveal whether the source follows a nearly circular path, moves through the habitable zone only briefly, or remains within it for most of its orbit. That uncertainty matters because climate depends on time as well as position. A world that spends only part of each orbit near temperate conditions may not resemble one that remains under steady heating. For a gas giant, the main atmospheric layers visible to a telescope may respond gradually, while any moons could experience more complicated seasonal cycles. The possible presence of moons is one reason a giant planet in a habitable zone attracts interest even when the planet itself is not Earth-like. In the solar system, the giant planets possess extensive satellite systems. Some moons are rocky, some icy, and several contain subsurface oceans maintained by internal heating. A Saturn-class world around Alpha Centauri A could, in principle, host large moons formed in a disk of material surrounding the young planet. If one of those moons were massive enough to retain an atmosphere and orbit far enough from damaging radiation belts, stellar heating might allow surface or near-surface liquid water. This is physically possible, but the present data says nothing direct about such moons. Webb would not resolve them from the planet at Alpha Centauri's distance. Their combined light would merge into the same point source. The idea belongs to the speculative layer of the interpretation, supported by knowledge of how giant planets often form satellite systems, but not by evidence from S1 itself. Habitability requires more than moderate energy from a star. A rocky world also needs suitable chemistry, a stable atmosphere, and conditions that allow liquid water to persist rather than appear briefly. Its mass affects whether gases escape. Its geological history influences how the atmosphere evolves. Impacts can remove volatiles or deliver them. In a binary system, long-term orbital stability adds another condition. Alpha Centauri B repeatedly changes its distance from Alpha Centauri A over the binary cycle, altering the gravitational environment and adding a smaller amount of changing light. A planet in a stable orbit around Alpha Centauri A must avoid paths that become strongly disturbed by the companion. Models indicate that stable planetary orbits are possible around each star within a limited region, including distances relevant to the proposed candidate. But stability does not guarantee a quiet climate. Slow gravitational effects can alter eccentricity and inclination over time. Those changes may vary the energy received and shape the architecture of any moons or neighboring planets. For S1, the possible orbit may be tilted or eccentric, making the word habitable even more conditional. A giant planet itself presents an environment unlike the surface of a rocky world. At the visible cloud tops, temperature and pressure may seem moderate in some regions, but there is no stable ground beneath them. Descending into the atmosphere would lead to increasing pressure, changing chemistry, and eventually states of matter that do not resemble ordinary gas or liquid. Hydrogen may become metallic deep inside, conducting electricity and helping generate a powerful magnetic field. Storm systems could persist for long periods. Cloud layers may contain compounds that condense at different depths. None of this makes the world uninteresting. It makes it a different class of environment. Habitability, as commonly discussed, is a surface concept shaped by terrestrial life, while a gas giant demands broader questions about chemistry in clouds, energy flow, and the limits of biological organization. The location near the habitable zone is scientifically meaningful because it helps define the planet's likely temperature and because it places the candidate in a part of the system where smaller worlds would be especially important. A confirmed giant planet could affect the prospects for those worlds through gravity. Depending on its mass and orbit, it might stabilize some regions, destabilize others, scatter planetesimals, or indicate that the protoplanetary disk contained enough material to build multiple planets. In the solar system, Jupiter's influence has been both protective and disruptive. It can deflect some comets, but it can also send small bodies inward. A similar giant around Alpha Centauri A would shape the delivery of water and impacts across any inner rocky system. Its existence would therefore change the context of habitability, even if the planet itself offered no habitable surface. It could be a source of stability in some arrangements, a source of disruption in others, or simply evidence that the system's formation history was rich enough to produce large worlds despite the nearby companion star. The phrase habitable zone also changes when viewed through the limits of direct imaging. Webb does not measure liquid water on S1. It does not detect continents, oceans, or even a complete spectrum. The candidate is inferred from thermal brightness at one mid-infrared wavelength and from its position relative to the star. The temperature near 225 Kelvin is an effective value shaped by models, not a reading from a surface. Clouds could make the atmosphere brighter or dimmer in the observed band. Internal heat could contribute to the emission. The true orbit could place the object outside the nominal zone for part of its path. Every step between the detected point and the phrase habitable world therefore adds assumptions. Scientific caution does not remove the significance of the location. It gives that significance the correct shape. S1 may occupy the nearest known example of a giant planet receiving roughly temperate levels of starlight from a close solar analog. That would be remarkable on its own. It would offer a nearby laboratory for studying a mature cold giant, its atmosphere, its possible moons, and its gravitational role in a binary star system. None of those possibilities requires the stronger claim that life has been found or that the planet resembles Earth. The most important result would be architectural rather than biological. A confirmed world there would show that a large planet can form, survive, and remain detectable within the dynamically complicated region around Alpha Centauri A. It would also make the unseen parts of the system more compelling, because one planet often turns an apparently empty star into a structure with history. The habitable zone does not answer the question of life. In this case, it marks the place where a more basic question has begun to take form: whether the nearest sun-like star is accompanied by a cold giant whose orbit may have shaped every smaller world that formed around it. The strongest test of S1 did not come from the first image. It came from the two images that followed and failed to show it. Webb returned to Alpha Centauri A in February and again in April of 2025. Months after the original August observation had revealed the compact mid-infrared source. By then, the candidate had acquired more than a position and a brightness. It had acquired expectations, If S1 were a planet bound to Alpha Centauri A, its orbit should carry it to a new location at a rate determined by its distance from the star's mass, and the geometry of the path. If it were a distant background source, Alpha Centauri's large proper motion should cause the apparent separation between them to change in a different way. If it were an optical residual or detector artifact, it might not return at all. Or it might reappear only when the telescope reproduced a similar instrumental configuration. Repeated observations were meant to separate these possibilities. Instead, they produced a more difficult result. The source was not recovered in either later visit. No convincing point appeared at the positions where the simplest orbital interpretations had led researchers to look. That absence immediately weakened the case for a planet. Because direct imaging depends on continuity. A real companion should not exist in only one frame of its history. It should move, brighten or dim within physical limits, and remain tied to the star across time. Yet a non-detection is not the same as proof that the first detection was false. Around Alpha Centauri A, the ability to see a planet changes sharply with position. The coronagraph blocks the central star, but it also creates an inner region where sensitivity falls and residual starlight becomes difficult to separate from a faint companion. A planet moving along its orbit can therefore become less detectable even while remaining present. The two later observations did not show an empty system in an absolute sense. They showed that no source matching S1 was recovered in the parts of the field where Webb had enough sensitivity to find it under those observing conditions. That distinction became the center of the mystery. The February visit occurred roughly half a year after the first detection, for a possible orbit lasting only a few years. That interval is long enough for substantial motion. The apparent path on the sky would depend on the inclination of the orbit, its eccentricity, the direction of motion, and the phase at which the planet was first seen. A nearly face-on orbit would trace a broad arc around the star. An edge on orbit could carry the object rapidly inward in projection, even if its true distance from the star remained large. An eccentric orbit could accelerate near the closest point and slow near the farthest. With only one detected position, many different paths could pass through the same point. The first image, therefore, did not predict one exact location for the second. It defined a family of possible locations, some of which remained observable and some of which approached regions dominated by stellar glare. By April, the allowed positions had shifted again. The second failed recovery did not simply repeat the February result. It removed more of the orbital possibilities that would have kept the planet visible, while leaving open paths that placed it closer to the coronagraph or behind structures of elevated noise. This is why the disappearance resisted a simple interpretation. If the candidate had been predicted to remain in a clean part of the image, and Webb had failed to detect it twice, the planetary explanation would have suffered a much sharper blow. Instead, the geometry allowed a real planet to move into places where the instrument was least capable of recovering it. The later observations therefore created two competing stories that both remained plausible. In one, S1 was a genuine planet that had crossed into Webb's difficult inner region. In the other, the August source was a residual feature that never represented a physical object at all. The data could not yet force a choice between them. The concept of a predicted position also required care. An orbit can be predicted precisely only after enough of it has been measured. A single point does not provide a velocity, a direction, or a curvature. It gives no direct way to distinguish a circular path from an eccentric one, or a low inclination from a steeply tilted orbit. Researchers had to combine the observed separation with assumptions about which orbits would remain stable around Alpha Centauri A and which masses and periods would be physically plausible. Those assumptions narrowed the field, but they could not replace a second detection. The failed visits thus exposed the difference between fitting an orbit and measuring one. Many mathematical paths could explain the first point and the later absences. Only a new point would begin to show which path, if any, the object actually followed. The disappearance also complicated the interpretation of the original significance. A signal between roughly 3.3 and 4.3 sigma is interesting enough to pursue, especially when it has the expected shape and lies at a plausible planetary separation. It is not so strong that later non-detections can be ignored. In a field shaped by residual speckles and imperfect subtraction, one persistent fluctuation may occasionally survive the processing. Repetition is what turns that possibility into a physical source. Without repetition, the statistical value remains tied to the assumptions used to describe the noise in the first epoch. The August observation may have captured a real point source. It may also have captured a rare arrangement of instrumental and stellar residuals that happen to resemble one. February and April did not reveal which. They only prevented the candidate from moving into the category of confirmed planets. The lack of recovery also ruled out some easier explanations. A stationary background source, bright enough to produce the August signal, might have been expected to remain visible at a shifted position once Alpha Centauri moved relative to the distant sky. If no appropriate source appeared along that expected background track, then a simple unrelated galaxy or star became less convincing. Although sensitivity variations and source confusion still had to be considered. Likewise, a bright, extended dust structure would not naturally vanish as a compact point unless the original processing had transformed it. The later images, therefore, did not erase all support for S1. They changed the balance among alternatives. The candidate became less like a straightforward object waiting to be confirmed, and more like an unresolved event whose meaning depended on orbital geometry and instrumental limits. This is an uncomfortable state in observational science because it offers neither discovery nor clean rejection. The most tempting interpretation remains visible, but so does the possibility that the signal was never astrophysical. The correct response is not to choose the more exciting story. It is to identify what future evidence would separate them. A reappearance at a position consistent with one of the surviving orbits would immediately strengthen the planetary case. The source would not need to return to its original location. It would need to move in a way that connects the epochs physically. Its brightness would also need to remain compatible with the same general class of cold giant, allowing for changes in viewing geometry and measurement uncertainty. A repeated absence during times when the candidate should be well outside the blind region would push the interpretation in the opposite direction. Each new visit, therefore, carries more value than the previous one because it tests a smaller set of possibilities. The two missing detections also reveal a broader limit of direct imaging. A planet can be bright enough to detect and still be difficult to confirm if its orbit repeatedly carries it through the instrument's least sensitive zones. This problem is especially severe for planets close to their stars, where the scientific reward is high, but the angular separation is small. Wide-orbit planets can remain visible through much of their paths. A world near the habitable zone of a nearby sun-like star may spend crucial intervals too close to the coronagraphic center, even when the telescope has already seen it once. S1, therefore, became a test not only of whether a planet exists around Alpha Centauri A, but of whether a single thermal detection can be turned into an orbital history with an instrument operating near its inner limit. By the end of the April observation, the situation had become more precise and less settled at the same time. The candidate had failed the simplest expectation of immediate recovery, yet it had not failed every physically plausible orbit. The later images removed certainty without removing possibility. S1 remained scientifically alive because its disappearance could be produced by motion into a region Webb could not examine well. It remained scientifically unconfirmed because that explanation had not been demonstrated by a new detection. The central mystery was no longer why a point appeared in August. It was whether the point had moved somewhere the telescope could not see, or whether it had never existed beyond the structure of that first image. The disappearance of S1 becomes less mysterious once the geometry of direct imaging is placed beside the geometry of an orbit. Webb does not see equally well at every distance from Alpha Centauri A. The coronagraph suppresses the star by covering its central image and controlling part of the surrounding diffraction. But the suppression is not uniform, very close to the star. Residual light remains intense and unstable. Slightly farther out, the instrument becomes more sensitive. Beyond that, other structures from the telescope, detector, and Alpha Centauri B begin to shape the field. The result is not a clear circular window around the star. It is a changing map of regions where a faint planet may be easy to recover, difficult to distinguish, or effectively hidden. If S1 is a real object moving on an orbit of only a few years, then several months are enough for it to cross from one of those regions into another. The August detection may therefore represent a brief interval when the planet stood far enough from the stellar glare in projection to become visible. By February and April, the same orbit could have carried it inward on the sky. Not necessarily inward in physical distance, but inward in apparent separation, placing it behind the brightest residuals near the coronagraph. This distinction between true distance and projected distance is central. A planet may remain nearly the same distance from its star while appearing to approach it from Earth because its motion turns along the line of sight. An orbit inclined to the plane of the sky can look compressed. At one phase, the planet appears near its greatest separation, where direct imaging has the best chance of finding it. As it continues around the star, its projected path bends inward, even though the three-dimensional orbit remains wide. If the orbit is seen close to edge-on, this effect can be severe. The object may spend long intervals apparently close to the star, cross behind or in front of it from Earth's perspective, and reappear only when its motion carries it outward again. A single observation near maximum apparent separation would then give a misleading impression of how often the planet should remain visible. The first detection could have caught S1 near the outer edge of its projected path, just before it entered a region where Webb's sensitivity declined sharply. Orbital simulations were used to test this possibility. Researchers generated many plausible paths that passed through the August position while remaining dynamically reasonable around Alpha Centauri A. Each simulated orbit had its own period: eccentricity, inclination, orientation, and orbital phase. Those paths were then advanced to the dates of the February and April observations. The predicted positions were compared with Webb's detection limits at each point in the field. Some simulated planets remained in clear regions and should have been recovered. Their absence made those paths less likely. Others moved close to the coronagraphic center or into areas where the residual stellar light was too strong. Those planets could escape detection even if their intrinsic infrared brightness remained unchanged. Across the surviving possibilities, the modeling suggested roughly a 52% chance that a planet matching S1 would be missed in both later observations. That probability does not mean there is a 52% chance that S1 is real. It answers a narrower question. Assuming the August source is a planet drawn from the allowed orbital models, there is a substantial probability that Webb would fail to see it during both return visits. The distinction prevents the simulation from being used as proof. It shows that the non-detections are compatible with a real orbit, not that they favor one automatically. The first signal still has to compete with instrumental and background explanations. Yet the calculation blocks the simplest rejection. A real planet would not necessarily remain visible. Its disappearance is not physically surprising once the blind region is included. The shape of that blind region is more complicated than a fixed dark disk placed over the star. Coronagraphic performance depends on direction as well as separation. Diffraction from Webb's segmented mirror produces structured residuals. The four-quadrant phase mask used by MIRI divides the field in a way that creates boundaries and regions of differing response. Pointing variations shift the star slightly relative to the mask. Alpha Centauri B contributes additional off-axis light whose pattern changes with telescope orientation. A position that is usable during one visit may be noisier during another, even at the same angular distance from Alpha Centauri A. The visibility of a planet, therefore, depends on the exact arrangement of orbit. Observatory orientation, binary geometry, and processing performance. The term blind region is useful, but it should not suggest a perfectly opaque and permanent area. It is better understood as a zone where the contrast becomes too poor for a source as faint as S1 to be recovered reliably. A brighter object might still be detected there. A fainter one might vanish farther out. The candidate sits close enough to Webb's sensitivity limit that small changes in background can determine whether it appears at all. Orbital speed adds another layer. If S1 follows a nearly circular path at a few astronomical units, its motion would be steady in physical space. But its apparent motion could still vary depending on perspective. If the orbit is eccentric, the planet would move faster near its closest approach to the star and slower near its farthest point. The August detection may have occurred near a part of the orbit where the object was both well separated in projection and moving toward a faster inner passage. In that case, the shift by February could be larger than a circular estimate would suggest. An eccentric path also changes the planet's temperature slightly as the amount of starlight rises and falls. Though a giant atmosphere may respond gradually rather than instantly, the candidate's brightness in the observed band could therefore change somewhat between visits. This effect alone would probably not explain a complete disappearance if the source remained in a clean region. But combined with poorer contrast, it could push an already marginal signal below the detection threshold. The simulations must therefore treat visibility as more than position. They have to consider whether the expected flux at each location would stand above the local noise. The missing detections also demonstrate why orbital recovery can require patience even for the nearest star system. A planet with a period of a few years does not offer unlimited observing opportunities. Webb can view Alpha Centauri only during certain seasonal windows because the telescope's sunshield must remain oriented to block the Sun, Earth, and Moon. The system cannot be observed continuously while the candidate moves. By the time the next window opens, the object may have crossed a large part of its projected orbit. Some positions may fall behind the coronagraph. Others may coincide with difficult diffraction features. A successful confirmation campaign therefore depends on predicting when the source is most likely to emerge into a favorable region again. The uncertainty in the orbit makes that prediction broad. Every non-detection removes some paths. But until the candidate is recovered, the remaining paths continue to spread across possible positions. The search becomes a narrowing exercise in which absence has value but does not provide the direction of motion. There is also an important asymmetry between detection and non-detection. One recovered point can establish a new location and immediately constrain a family of orbits. A missing point only states that the object was not bright enough to be identified where the instrument could see. If much of the allowed orbital region is poorly accessible, the absence carries limited information. This is why the 52% estimate matters. It quantifies how much of the plausible planetary scenario remains hidden from the later observations. The number is not small enough for the non-detections to be surprising, and not large enough for them to be irrelevant. Nearly half of the simulated cases should have produced a visible source, which means the failed recoveries do place pressure on the planetary interpretation. Slightly more than half could escape both visits, which means that pressure is not decisive. S1 remains suspended between these proportions. The orbit required to hide it does not need to violate known physics or demand an impossible arrangement. It needs only to belong to the portion of allowed paths that carry the candidate into Webb's least sensitive region at the relevant times. The same reasoning produces a testable consequence. A planet cannot remain hidden forever unless its orbit is oriented so that most of its projected path lies near the star. If S1 was visible at 1.5 arcseconds in August, then the orbit must eventually carry it back toward a comparable separation, although the timing depends on the period and direction of motion. Future observations can target windows when many surviving orbits predict that outward return. A repeated detection at the expected brightness would connect the missing interval into a coherent path. The disappearance would then become evidence of orbital geometry rather than evidence against the source. Continued absence during favorable predicted windows would do the opposite, gradually forcing the candidate explanation into narrower and less likely configurations. The blind region therefore delays judgment, but it does not make the question unanswerable. It turns confirmation into a problem of timing. S1 may have vanished because the first observation caught a false residual that never moved anywhere. It may also have vanished because a real world followed its orbit into a part of the image where Webb could no longer separate it from its star. The available simulations show that the second possibility is common enough to remain serious. What appears as absence in the processed images may be only the temporary loss of contrast, a planet continuing along an ordinary path while the instrument waits for geometry to make it visible again. 5 years before S1 appeared in Webb's mid-infrared data, another possible source had already been reported near Alpha Centauri A. It was labeled C1 and emerged from observations made in 2019 with the Very Large Telescope in Chile. The instrument used for that search worked in the thermal infrared and was designed to suppress the glare of the star while looking for cool planetary emission close beside it. Like S1, C1 was not an image of a resolved world. It was a faint feature in a difficult field, recovered only after careful processing and never confirmed through repeated detection. At the time, the source was treated as intriguing but uncertain. It could have represented a planet, a dust structure, a background object, or a residual produced by the instrument and the subtraction of starlight. The later appearance of S1 changed the context. Once Webb found a second candidate source in the same system, at a different position, and several years later, the possibility emerged that the two detections might not be separate events at all. They might be 2 points along the orbit of one unseen planet. This idea is attractive because planets move, and because the interval between the observations is long enough for a world on a compact orbit around Alpha Centauri A to travel through a substantial fraction of its path. Yet the connection remains a hypothesis built from limited evidence. C1 and S1 were measured by different telescopes at different wavelengths, with different coronagraphs, detectors, and processing methods. Each source carries its own uncertainties. Linking them does not simply add 2 weak detections together. It requires showing that one physical orbit can pass through both measured positions at the correct times while remaining stable in the binary system and consistent with the later non-detections. The first step is geometric. A candidate planet, seen near Alpha Centauri A in 2019, must move to the position of S1 by August 2024. That gives the orbit a time interval and two projected locations, but not a unique solution. Many three-dimensional paths can appear as the same 2 points on the sky. The orbit can be tilted toward Earth, rotated around the star, stretched by eccentricity, or viewed near different phases. Its true distance from Alpha Centauri A can be larger than the measured projected separation at either epoch. The direction of travel is also not directly known from isolated detections. A path connecting C1 to S1 in one direction may have a counterpart moving the opposite way through a different part of the orbit. Researchers therefore explore families of solutions rather than drawing a single ellipse through the data. The relevant question is whether plausible paths exist, not whether the 2 points force one obvious orbit. According to the candidate models, such paths do exist. Some orbital configurations can place the same object near the C1 location in 2019 and near S1 more than 5 years later. Because the proposed orbital period may be only a few years, the planet could have completed more than one revolution between the two observations. This possibility makes the connection less visually intuitive. The object would not simply drift in a slow arc from one point to the other. It might circle Alpha Centauri A once or twice, returning to a different projected position because the observations occurred at different orbital phases. A period near 2 or 3 years allows several combinations of completed cycles and partial cycles across the interval. The exact count depends on the fitted orbit. This freedom helps the hypothesis survive, but it also reduces its power when many possible orbital periods and orientations can connect two uncertain sources. Agreement alone is not strong evidence that the sources are identical. The link becomes more meaningful only if the same orbit also explains why S1 was absent in February and April of 2025. Some solutions do this by carrying the planet into Webb's inner region of poor sensitivity. A single orbit can therefore be constructed that joins C1, S1, and the later non-detections into one continuous history, visible with the Very Large Telescope, visible years later with Webb, then temporarily hidden near the star. This is a coherent interpretation. But coherence can arise because the model has enough adjustable parameters. The orbit must be tested by predictions it has not already been shaped to match. C1 itself has a complicated status. The source was found in observations aimed at detecting thermal emission from planets around Alpha Centauri A, but it did not reach the level of a confirmed companion. Its appearance was close to the limits of the data, and alternative explanations remained. Thermal infrared images from the ground face backgrounds, far brighter than those encountered by a cold space telescope. Earth's atmosphere and the telescope structure emit strongly at these wavelengths. Rapid changes in atmospheric turbulence alter the star's point spread function. Coronagraphic subtraction can leave residual features whose shapes depend on observing conditions and data processing. The Very Large Telescope observation used sophisticated techniques to control these effects, yet a faint source detected once cannot escape them completely. If C1 was not astrophysical, then any orbit linking it to S1 would be a mathematical coincidence. The same caution applies in the opposite direction. If S1 was an instrumental residual, the existence of C1 cannot rescue it. Two uncertain sources become compelling only when an independent physical relationship is demonstrated. Their possible brightnesses add another test. A mature giant planet should produce thermal emission that follows a physically reasonable spectrum. The Very Large Telescope and Webb did not observe in exactly the same band, so the measured fluxes cannot be compared as though they were identical readings. Atmospheric absorption, cloud layers, and the planet's temperature can change the brightness across the infrared. A source that is detectable at one wavelength may be weaker at another. Instrument sensitivity and processing losses differ as well. Models must therefore ask whether one planet with a consistent radius, temperature, and atmosphere could plausibly generate both signals after each instrument's response is included. The available interpretation suggests that this is possible, but the evidence remains too limited for a unique atmospheric model. The comparison supports compatibility rather than identity. Proper motion provides a more direct line of reasoning. Alpha Centauri moves quickly against the distant background sky. A fixed background source seen in 2019 would not remain at the same relative position years later. By 2024, the star would have shifted far enough that a remote galaxy or unrelated object should appear in a predictably different place relative to it. If C1 and S1 were the same stationary background source, their observed positions would need to match that track. The proposed connection instead treats them as a bound companion, moving with Alpha Centauri A, while also orbiting it. This can be tested because the star's proper motion is well known. The geometry does not automatically prove the planetary interpretation, but it helps rule out simple versions of a background explanation. A true planet should share the system's overall motion across the sky. A distant object should remain fixed while Alpha Centauri passes in front of it. Future observations can separate these cases much more cleanly if the candidate reappears. The deeper value of the C1 connection is that it extends the possible timeline. S1 by itself provides one position, C1. If related, adds a second position separated by years. 2 points do not define a complete orbit, but they constrain it far more than one. They can narrow the range of periods, orientation, and eccentricities that remain plausible. They can also identify future dates when the object should emerge from Webb's blind region. The orbit then becomes a predictive framework rather than a retrospective fit. A new detection at one of those predicted locations would do more than confirm S1. It would strengthen the case that C1 was an earlier observation of the same world, turning two isolated anomalies into a measurable planetary trajectory. A detection somewhere incompatible with the linked orbit would weaken the connection while possibly preserving S1 as a separate object. Continued absence would gradually make both interpretations harder to sustain. The scientific temptation is to treat C1 as a forgotten first glimpse and S1 as the rediscovery. That narrative is possible, but the evidence has not earned it yet. The two sources were found under different conditions. Neither was repeated immediately, and the orbit joining them is one member of a broad family of models. Their relationship is therefore best described as a testable alignment. The positions, timing, and possible periods allow one planet to explain both. The later non-detections do not eliminate that picture. What remains missing is the next point, a source recovered where the shared orbit says it should be. Until then, C1 and S1 remain two suggestive marks separated by 5 years. Close enough in possibility to belong to one world, but not yet connected by motion. If S1 and C1 belong to the same object, the orbit that joins them does not resemble the simplest path astronomers might first expect around Alpha Centauri A. The allowed solutions tend toward periods of roughly 2 to 3 years. Yet period alone does not describe the difficulty. A circular orbit lying neatly in the same plane as the Alpha Centauri binary would place the candidate in a relatively orderly architecture. The available positions and later non-detections instead permit paths that are more eccentric, more steeply tilted, or both. Eccentricity measures how far an orbit departs from a circle. A low eccentricity path keeps the planet at nearly the same distance from its star throughout each revolution. A high eccentricity path stretches into an ellipse, carrying the planet through a closer, faster passage near the star and a farther, slower passage on the opposite side. Inclination describes how the orbital plane is tilted relative to a chosen reference plane. In this case, the important comparison is with the broad orbital plane of Alpha Centauri A and Alpha Centauri B. A strongly inclined planet would travel on a path that cuts across that binary plane rather than remaining aligned with it. These two properties can change almost every part of the observational story. They alter where the planet appears on the sky, how quickly it seems to move, how much starlight it receives, and how often it enters the regions where Webb has difficulty seeing it. The suggested period follows naturally from the candidate's apparent separation and the mass of Alpha Centauri A, a planet at a few astronomical units from a star slightly more massive than the Sun should complete an orbit in only a few years. Kepler's laws connect orbital period with distance and stellar mass. So a compact path around Alpha Centauri A is expected to move much faster than Jupiter moves around the Sun. This makes the months between the August, February, and April observations dynamically important. S1 would not be almost stationary. It could advance through a large fraction of its apparent orbit, especially if the path is eccentric and the planet was moving through a faster section. A period near 2 or 3 years also helps explain how a source seen by the Very Large Telescope in 2019 might reappear in a different position in 2024. The object could complete one or more revolutions between those epochs, depending on the exact period, before reaching the location identified by Webb. This gives the model enough freedom to link C1 and S1, but it also creates uncertainty because several different cycle counts may fit the same pair of observations. The orbit is not being traced continuously. It is being reconstructed from isolated points and absences, which allows multiple paths to pass through the available constraints. Eccentricity can make those paths more flexible. A planet on an elongated orbit does not spend equal time in equal stretches of apparent distance from the star. It moves rapidly near periastron, the closest point in its orbit, and slowly near apastron, the farthest point. If the August detection occurred closer to apastron, S1 could have appeared well separated from Alpha Centauri A and moved relatively slowly for a time. As it began falling inward, its orbital speed would increase. By the later Webb visits, the candidate might have reached a much smaller projected separation, entering the glare-dominated region near the coronagraph. If instead the first detection occurred on another part of the ellipse, perspective could still produce a similar inward motion on the sky. The exact sequence depends on how the ellipse is turned in 3 dimensions. This is why eccentricity and inclination cannot be interpreted separately. An elongated orbit, viewed nearly face-on, may still appear broad and easy to follow. A more circular orbit viewed nearly edge-on can appear to collapse toward the star. A tilted eccentric orbit can combine both effects, producing long intervals of favorable separation and short intervals of rapid disappearance. The possible strong tilt relative to the binary plane is especially interesting because planetary systems often preserve some memory of the disk in which they formed. Stars and planets usually emerge from rotating material, and the angular momentum of that material tends to establish a preferred plane. In a simple single-star system, large planets are often found on roughly aligned orbits, although later interactions can disturb them. Around Alpha Centauri A, the presence of Alpha Centauri B complicates that expectation. The companion star can truncate the original planet-forming disk, stir material within it, and impose long-term gravitational torques on any planets that survive. So, a strongly misaligned orbit would demand an explanation. It could indicate that the disk itself formed with a tilt relative to the binary, that interactions with other planets reshaped the system, or that the candidate's orbit evolved through the influence of Alpha Centauri B over immense periods. None of these possibilities can be selected from the present data. They show only why orbital orientation carries information about history. The binary companion does more than provide a tilted reference plane. It also limits which planetary orbits remain stable. Alpha Centauri A and B move around each other on an eccentric path, so their separation changes significantly over the binary cycle. A planet orbiting Alpha Centauri A must remain close enough to its host that the gravity of Alpha Centauri B does not repeatedly pull it into an unstable trajectory. Numerical studies indicate that stable regions exist around each star, including distances relevant to S1, but stability depends on eccentricity, inclination, and orientation. A moderately tilted planet may remain bound for billions of years. A more extreme path can experience gradual changes in eccentricity and inclination through secular perturbations, long-term gravitational effects that accumulate over many orbits. Under some configurations, the planet's orbital shape and tilt can exchange with one another in cycles, pushing the world periodically closer to or farther from its star. The candidate models do not prove that such cycles are occurring, but they place S1 in a setting where the binary star cannot be treated as a distant decoration. It is part of the planet's dynamical environment. A strange orbit would therefore not necessarily mean an impossible orbit. It would mean an orbit whose long-term survival and origin have to be tested in the full three-body system. The possible eccentricity also changes the interpretation of habitability. A giant planet crossing the nominal habitable zone on an elongated path may receive very different levels of starlight during each revolution. Near the closest approach, its atmosphere would absorb more energy. Near the farthest point, it would cool. A massive atmosphere has substantial thermal inertia, so the visible temperature may respond more slowly than the changing orbit. Any moons could experience stronger seasonal forcing, especially if their climates react more quickly. The phrase habitable zone then becomes less like a fixed address and more like a region the planet may enter and leave. This does not make the candidate less important, but it makes its environmental description more dynamic. A world can be observed at a projected distance associated with temperate heating while spending much of its orbit under different conditions. Only a measured orbit can reveal the average energy received and the range around that average. The orbital models also affect the predicted brightness of S1. If the planet moves significantly closer to Alpha Centauri A, additional stellar heating may raise the temperature of its upper atmosphere. The effect at 15.5 micrometers would depend on clouds, chemistry, and how quickly heat is redistributed. If it moves farther out, the planet may cool slightly, though internal heat could reduce the change. These variations are likely smaller than the contrast loss caused by approaching the star, but they could matter near the detection threshold. A planet hidden in February or April may have been not only closer in projection, but also somewhat different in thermal emission. Future observations at several wavelengths could distinguish orbital brightness changes from instrumental sensitivity changes, though such measurements would require the source to be recovered first. Until then, the orbit remains the most important missing physical quantity. It determines mass estimates when combined with radial velocity or astrometry. It determines whether C1 and S1 can truly be connected. It determines when Webb should look again and where the point source should reappear. It also determines whether the candidate belongs to a stable and understandable architecture or occupies a path shaped by a more violent past. A second confirmed position would narrow the possibilities sharply by adding direction and speed. A third would begin to reveal curvature. With enough measurements, the eccentricity and inclination would move from flexible model parameters to properties of a real world. At present, the unusual orbit is not itself an observed fact. It is the kind of orbit that remains available after the existing detections and non-detections are forced into one consistent picture. That picture is compelling because it explains several difficult features at once, yet it remains broad enough to warn against certainty. S1 may be following a compact, tilted, eccentric path that repeatedly carries it through Webb's blind region and across the habitable zone of Alpha Centauri A. Or the appearance of such a path may be the mathematical shadow cast by too little data. The next recovered point would decide whether the orbit is genuinely strange or merely the temporary shape of uncertainty. If S1 is confirmed, the importance of the result will extend far beyond the addition of one more planet to an already crowded catalog. The candidate would become one of the nearest directly imaged planets ever found, and one of the closest to its host star, in angular and physical separation around a mature sun-like star. Most directly imaged exoplanets are young, hot, and widely separated from their stars. Their youth makes them luminous in the infrared, and their broad orbits make them easier to distinguish from stellar glare. S1 would occupy a different regime. It would be old, comparatively cold, and located only a few astronomical units from Alpha Centauri A, a star whose age and basic character resemble those of the Sun. Confirming such a world would show that direct imaging no longer belongs only to distant, youthful systems with unusually favorable geometry. It would demonstrate that a mature giant planet in a compact orbit around a nearby solar analog can be isolated through its own thermal emission, even when a second bright star complicates the field. That shift would be both technical and scientific. Technically, it would validate a method of using Webb's mid-infrared sensitivity, coronagraphy, and detailed binary star modeling to reach a class of planets that earlier instruments could not separate reliably. Scientifically, it would open a nearby planetary system whose architecture has remained hidden despite decades of searching. The distinction matters because direct imaging provides information that indirect techniques cannot obtain in the same way. Radial velocity reveals the gravitational pull of a planet on its star. Astrometry measures the star's motion across the sky. Transits reveal a planet only when its orbit carries it across the stellar disk from Earth's perspective. Direct imaging separates the planet's light from the star's light. Once that separation is achieved, the planet can be studied as an object rather than only as a gravitational influence. Its brightness can be measured at different wavelengths. Its temperature can be estimated. Atmospheric gases and clouds may eventually leave identifiable features in a spectrum. Repeated positions can trace the orbit. Changes in brightness may reveal weather, rotation, or seasonal heating, although those goals would remain demanding for a source as faint as S1. Confirmation would therefore transform the candidate from a single unexplained point into a target for physical characterization. The nearest distance would magnify the value of every later observation. Alpha Centauri is about 4.3 light-years away, so a planetary orbit of a few astronomical units spans a relatively large angle on the sky, compared with the same orbit around a more distant star. That angular scale gives future telescopes a better chance to separate the planet from its host and perhaps to observe it at several points in its orbit. The system could become a calibration ground for techniques intended to find colder and smaller worlds. Instruments could test how well orbital motion, thermal brightness, and atmospheric models agree when the target is close enough for repeated, high-precision study. Even a gas giant would provide an essential step toward the much harder task of imaging rocky planets around sun-like stars. It would show how starlight subtraction behaves in a mature system, how planets move through coronagraphic blind regions, and how much information can be recovered from weak thermal signals near the edge of detectability. A confirmed S1 would also change the planetary history inferred for Alpha Centauri A. Until now, the bright pair has offered more limits than discoveries. Searches have ruled out some types of planets and produced several candidates that failed to survive later scrutiny. A verified giant would prove that planet formation succeeded around Alpha Centauri A, despite the presence of Alpha Centauri B. This would place constraints on the original disk of gas and dust. The disk must have contained enough material, remained stable long enough, and supported growth fast enough for a massive planetary core to form before the gas dispersed. The binary companion may have truncated the outer disk or stirred its contents. But those effects would not have prevented the assembly of at least one large world. The planet's orbit would then reveal how that world survived. A nearly circular and aligned path might suggest relatively calm evolution. A highly eccentric or tilted orbit could point toward later gravitational interactions, either with Alpha Centauri B or with other planets that are no longer visible. In that way, confirmation would not simply identify what is present. It would begin to reconstruct what happened. The existence of one giant planet would also alter expectations for additional worlds. Planetary systems rarely form one object in complete isolation. A disk capable of building a Saturn-class planet may also have produced rocky planets, smaller gas-rich worlds, belts of debris, or moons. None of these companions would be guaranteed, and the giant itself could have disrupted some of them. Yet the discovery would replace the assumption of an empty system with evidence of a structured one. Future radial velocity and astrometric searches could be designed around the known giant's orbit, removing its signal and looking for smaller perturbations. Direct imaging could target regions where stable companions are most likely. Dust measurements could search for belts shaped by the planet's gravity. The candidate's confirmation would therefore reorganize the search strategy around Alpha Centauri A. Instead of asking whether planets formed there at all, astronomers could ask how many formed, where they remain, and how the binary companion shaped their survival. The potential effect on studies of habitability would be indirect but important. S1 itself is likely a gas giant with no Earth-like surface. Its location near the habitable zone would not make it a second Earth. However, its gravity could influence any rocky worlds or moons in the same system. A giant planet can scatter small bodies, reshape asteroid belts, alter impact rates, and change the long-term stability of neighboring orbits. Depending on its exact path, it might leave room for stable terrestrial planets closer to Alpha Centauri A, or it might disturb them. If it carries large moons, those moons could receive moderate stellar energy, though no current observation can test their existence. The orbital solution would determine which of these possibilities remain physically reasonable. A confirmed planet with a compact and stable orbit could make the system more promising for future habitability studies by defining where smaller worlds might persist. A strongly eccentric or inclined giant could make the architecture more complicated while revealing a history of migration or dynamical disturbance. Either outcome would be scientifically valuable because it would replace speculation with a measurable gravitational framework. Confirmation would also validate Webb's ability to detect mature, cold planets in nearby systems through mid-infrared emission. That capability was not guaranteed simply because the telescope possessed a large mirror and a coronagraph. Alpha Centauri A pushes the instrument into an extreme combination of brightness, close angular separation, and binary contamination. Recovering the same source across multiple epochs would show that the processing can distinguish a real moving planet from residual starlight and detector structure. It would demonstrate that the elaborate subtraction of two stars has preserved a faint astrophysical signal rather than manufacturing one. This would influence the design of future observing programs. Other nearby stars could be searched with greater confidence. Strategies could be built around repeated visits, timed to avoid blind regions. Reference star selection, telescope orientation, and artificial planet tests could be refined using a confirmed case. The result would become a benchmark for future observatories designed specifically to image planets around Sun like stars. Those missions will need to suppress starlight more deeply and reach worlds much smaller than S1. A nearby cold giant would provide a real system in which to practice orbital recovery, spectral extraction, and long-term monitoring before that next generation begins. The discovery would also carry a particular symbolic weight because of the star involved, though the science would remain more important than the symbolism. Alpha Centauri A is not an anonymous point in a distant survey. It is the nearest close relative of the Sun and part of the stellar system most often imagined as the first destination beyond the solar system. A confirmed planet there would give the nearest neighboring suns a known architecture. It would turn a familiar name into a place with at least one mapped world. That emotional significance should not be confused with evidence of life or resemblance to Earth. But it explains why the result would resonate beyond exoplanet science. The nearest planetary systems serve as bridges between abstract statistics and specific environments. They are close enough for repeated study and distant enough to preserve the full difficulty of interstellar space. S1, if real, would stand at that boundary. Its confirmation would not solve the mystery of whether Alpha Centauri contains habitable worlds. It would establish something more basic and more durable, that Webb can isolate the heat of a mature planet beside the nearest sun-like star, and that the long hidden planetary history of Alpha Centauri A has finally begun to come into view. The next decisive step for S1 is not a more elaborate interpretation of the existing data. It is another detection. Until the source appears again at a position compatible with orbital motion around Alpha Centauri A, every model remains provisional, no matter how well it can connect the August observation, the later absences, and the earlier C1 candidate. A planet is defined not only by its brightness or by the plausibility of its temperature, it is defined by motion under gravity. Repeated imaging must therefore show that the source changes position in a way that belongs to Alpha Centauri A rather than to the background sky. The telescope, or the processing itself. The source must reappear at a location fitting a physically reasonable orbit and with brightness compatible with a cold giant planet. Its movement must share the large proper motion of the Alpha Centauri system while also tracing a smaller orbit around the primary star. Only when these conditions begin to overlap can S1 move from candidate to confirmed planet. The most valuable future observation would place Webb on the system when many of the surviving orbital solutions predict that the object should be outside the coronagraph's most difficult inner region. A detection during such a window would provide a second secure point after August and would immediately eliminate a large fraction of the possible paths. The direction of travel would become measurable. The apparent speed would constrain the period. The change in separation would begin distinguishing a circular orbit from an eccentric one, and the orientation of the motion would narrow the inclination. If the new position also connected naturally with C1, the earlier Very Large Telescope source would gain importance as a possible first epoch rather than remaining an isolated anomaly. If it did not, S1 could still be real, but the proposed link between the two candidates would weaken. This is why timing matters more than simply gathering more images. A visit made while most allowed orbits remain hidden near the star may add little. A visit aimed at a predicted reappearance can test the planetary hypothesis directly. Common proper motion would provide one of the clearest forms of confirmation. Alpha Centauri A moves rapidly across the distant sky. so a background galaxy or unrelated infrared source should not remain fixed beside it. Over time, the star's position shifts relative to those remote objects. A bound planet, by contrast, travels with the system while moving around the star. Repeated measurements can separate these two motions. The broad shared movement identifies the source as part of Alpha Centauri rather than the background, while the smaller curve displacement reveals the orbit. A source that continues to follow Alpha Centauri A through successive epochs becomes increasingly difficult to explain as a chance alignment. A source that stays fixed against the background would gradually separate from the star along a predictable track. One recovery would begin this comparison, while several would be difficult for an artifact or distant object to imitate. Astrometry, the precise measurement of position, would then turn the candidate into a dynamical system. Each point on the sky would carry uncertainty from the telescope's pointing, the coronagraph, the point spread function, and the image processing. Those uncertainties must be small enough to distinguish real orbital curvature from measurement scatter. With enough epochs, researchers could fit the semi-major axis, eccentricity, inclination, and orientation of the orbit. The period would follow from the repeating motion and the known mass of Alpha Centauri A if C1 belongs to the same object. The longer time baseline would improve the fit substantially. If it does not, Webb alone could still build the orbit over future years. A reliable orbit would resolve several questions at once. It would reveal how often the planet enters the nominal habitable zone, whether it remains dynamically stable under the influence of Alpha Centauri B, and when it should become easiest to observe again. It would also provide the framework needed to interpret every other measurement. Brightness without distance from the star is incomplete. Temperature without orbital phase can be misleading. A spectrum without a mass estimate can fit too many atmospheric models. The orbit gives these measurements a physical context. Spectroscopy would be the next major step, though it would be more difficult than detection. A spectrum separates the candidate's light by wavelength, allowing molecular features and cloud effects to alter the shape of the measured emission. For a cold, giant planet, gases such as methane, water vapor, ammonia, carbon monoxide, and carbon dioxide may leave signatures in the infrared. Depending on temperature and atmospheric mixing, clouds could flatten or reshape those features. The planet's internal heat and the energy received from Alpha Centauri A would together determine which atmospheric layers are visible. A single band near 15.5 micrometers cannot resolve these possibilities. Measurements across several wavelengths could test whether the source follows a planetary thermal spectrum or resembles a background galaxy. Dust structure, or instrumental residual. Even limited spectral information would help distinguish a cool, large planet from a warmer, smaller source. A full atmospheric characterization may remain beyond Webb if the contrast is too difficult. But color measurements from multiple filters could still narrow the temperature and radius. Radial velocity observations would approach the candidate from a different direction. A massive planet pulls Alpha Centauri A back and forth as both bodies orbit their shared center of mass. That motion shifts the star's spectral lines slightly toward and away from Earth. For a Saturn-class object on a period of a few years, the signal may be detectable in principle. But the binary system makes the analysis demanding. The motion caused by Alpha Centauri B is vastly larger and must be modeled with exceptional precision. Stellar activity can add smaller variations. Instrumental stability must be maintained across years. Yet, a radial velocity pattern with the same period and phase as the imaged orbit would be powerful evidence. It would also provide a minimum mass, while the inclination from direct imaging would allow the true mass to be calculated. That combination would test whether the thermal brightness really corresponds to a Saturn-class planet or whether the atmospheric models have misestimated its properties. Astrometry of the star could offer another mass measurement. A planet massive enough to produce the observed infrared flux should cause Alpha Centauri A to trace a tiny reflex orbit on the sky. Detecting that motion requires separating it from parallax, proper motion, and the binary orbit. But the system's nearness helps because a given physical displacement appears larger than it would around a distant star. Long-term positional measurements from space and the ground may therefore contribute even if no single dataset is decisive. The strongest result would come from agreement among methods. Direct imaging would show the planet's changing position. Radial velocity would reveal motion along the line of sight. Stellar astrometry would measure motion across the sky. Together, they could determine the three-dimensional orbit and dynamical mass. Spectral measurements could then describe the atmosphere without relying entirely on evolutionary models. This convergence also guards against the weaknesses of each technique. Imaging can be confused by residual light. Radial velocity can be confused by stellar activity and binary motion. Astrometry can be distorted by incomplete orbital coverage. When all three point to the same period, phase, and mass, the alternatives become much harder to sustain. Continued non-detection would also produce a result, though not the one implied by the first image. If Webb returns during several favorable windows and S1 remains absent where the surviving orbits predict it should be visible, the planetary interpretation will gradually lose credibility. The source may then be understood as a rare residual produced by the combination of two bright stars, the coronagraph, and the processing pipeline. That outcome would still matter. It would reveal where the limits of mid-infrared, high-contrast imaging become vulnerable to false positives and would improve future searches around other nearby stars. The August feature would become a calibration lesson, showing how a candidate can survive multiple reductions and still fail the test of time. Science advances through such limits as well as through discoveries. The conclusion cannot be chosen in advance. S1 must be allowed either to return as a moving object or to fade under increasingly restrictive tests. Until that happens, its correct name remains candidate. The word preserves both possibilities. It acknowledges that the source has enough planetary characteristics to justify continued observation, while recognizing that one epoch cannot establish an orbit, a mass, or even a physical existence beyond the original image. The unresolved quality of S1 is therefore not a failure of explanation. It is the exact boundary of the evidence. Researchers can explain how a real planet might disappear into Webb's blind region. They can explain how the observed brightness might arise from a cold giant. They can construct orbits that connect S1 with C1 and remain stable around Alpha Centauri A. What they cannot yet show is that the source has moved along any one of those paths. The final answer will not come from a more persuasive story. It will come from a point of light returning where gravity says it should be, carrying the motion of Alpha Centauri across the sky and the smaller curve of its own orbit within the nearest neighboring system. The light from Alpha Centauri has crossed more than 4 years of interstellar space before reaching the instruments that separate one faint source from the glare of two neighboring suns. Within that light, S1 remains neither a discovery nor a mistake, but a possibility held carefully at the edge of what the evidence can support. It may be a cold giant planet moving through an orbit that briefly carried it into view and then returned it to the brightness surrounding Alpha Centauri A. It may be a residual pattern created by a telescope working close to the limits of its design. For now, both interpretations remain open, and the system continues along its quiet motion regardless of which one is true. Alpha Centauri A and B keep circling their shared center of mass. Proxima Centauri continues along its distant path. Any planets around them move through years that pass unseen between brief observing windows. The unanswered question is therefore not frozen in one image. It is unfolding in real time. Through gravity, motion, heat, and distance, future observations may recover the point and connect it to an orbit, giving the nearest sun-like star its first confirmed directly imaged world, or they may leave the field empty, turning S1 into a lesson about how closely a false signal can resemble a planet. Either outcome will sharpen the search. Science often advances this way, not through immediate certainty, but through signals that remain unresolved until nature repeats them. Somewhere beside Alpha Centauri A, a real world may be continuing through the darkness between observations, carrying no awareness of the attention directed toward it. The instruments will return when geometry allows, and the star will once again be dimmed so that something smaller may be seen. Until then, the candidate remains where careful science leaves it possible, unconfirmed, and still moving through the nearest unknown planetary system.